Welcome friends, Igor is here, and in this video we will derive an efficient way to compute determinants using elementary row operations. In this lesson we will lay all the necessary theoretical groundwork for a more efficient approach to computing determinants. We will learn how elementary row operations affect the determinant of a matrix. Let's get started. First, let's prove that if a square matrix has a 0 row or a 0 column, then its determinant is equal to 0. Let's say A is a square matrix of size n, and row I of this matrix is the 0 row. Then we can compute the determinant of this matrix using the cofactor expansion along row I. But our assumption says that every entry in row I is equal to 0. Therefore, this sum becomes 0. If the matrix A has a 0 column, then take the transpose of this matrix. The transposed matrix has the 0 row, therefore its determinant is equal to 0 by what we just proved. But then we also established in the previous video that taking the transpose does not change the determinant. Therefore, the determinant of the matrix A is equal to 0. Here is a preview of our upcoming efficient way to compute matrix determinants. Before applying the cofactor expansion formula, we will apply some row operations to the matrix. Our goal would be to reduce this matrix to the so-called upper triangular form, because as we will see, it is easy to compute determinants of matrices in the upper triangular form. But in order to realize this approach, we need to learn how performing row operations affects the determinant of the matrix. There are three types of elementary row operations: swap, scale, and replacement. Therefore, we will take one row operation at a time, and we will see what happens to the determinant of the matrix. First, let's prove that if you swap the location of two rows in a matrix, then the determinant changes the sign. The same rule applies to swapping two columns of a matrix. To prove this result, first, let's consider a special case. Let's suppose that the matrix B is obtained from the matrix A by swapping locations of two adjacent rows, let's say row I and row I plus 1. This assumption means that the submatrix, which is obtained from the matrix B by deleting row I plus 1 and column J, is the same as the submatrix which is obtained from A by deleting row I and column J. It is crucial here that we are swapping two adjacent rows. Also, the entries in row I plus 1 of the matrix B are the same as entries in row I of the matrix A. To compute the determinant of B, we use the cofactor expansion along row I plus 1. Then we apply our previous observation on the submatrices and the entries in rows I plus 1 and I. In the last sum, let's factor out a copy of -1 in each term. Then we can factor out this copy of -1 in front of the entire sum, and what's left inside is the cofactor expansion formula for the determinant of A along row I. Therefore, this sum is the determinant of A, and it's multiplied by -1. So we have proved that swapping two rows changes the sign of the determinant, but only in a special case when you swap two adjacent rows. We still need to figure out what happens in the general case. In general, let's assume that the matrix B is obtained by swapping two arbitrary rows of matrix A, let's say rows S and T, with S less than T. Then the trick is to observe that this swap can be obtained as a sequence of swaps of adjacent rows. Here's how to do this. We start with row S, which is located above row T, and we repeatedly swap this row with each row below this until we reach row T. We swap row S with row T, and we stop there. This requires T minus S row swaps. Now, row number T sits in position T minus 1, and we swap this row with each row above it until it sets into position S. This requires T minus S minus 1 swaps. As a result of this procedure, all rows between S and T were moved one place up in the first part and then one place down in the second part. In essence, they all came back to their original location, and the only rows that changed their positions are rows S and T. They got swapped. So, we can achieve the swap of rows S and T as a sequence of swapping adjacent rows, and the total number of these adjacent row swaps is 2 times T minus S minus 1. However, we just established that if you swap two adjacent rows, then the determinant changes the sign. But now you see that no matter what S and T are, swapping these two rows requires an odd number of adjacent row swaps. Therefore, the determinant will change the sign. To see that it also works for columns, take the transpose. We know that taking transpose does not change the determinant, and in the transpose, swapping columns is actually swapping rows. Next comes the scale operation, and we are going to prove that if you scale a row or a column of a matrix by scalar alpha, then you scale the entire determinant by alpha. Suppose A is a square matrix of size n, and the matrix B is obtained from A by scaling row I by the scalar alpha. Let's observe that it is only the row I that has changed. Therefore, the other rows are the same. So if you look at the submatrices of A and B, which have row I deleted, then the submatrices are equal. With this observation in mind, we are going to compute the determinant of B using cofactor expansion along row I. These two submatrices are equal to each other, and the entry in position ij of the matrix B is the entry in position ij of the matrix A multiplied by alpha. Each term in this sum is multiplied by alpha, therefore we can factor alpha out in front of the entire sum. This sum now represents the cofactor expansion for the determinant of A along row I. And we see that if we scale a row of matrix A by alpha, then we scale the determinant of A by alpha. The same is also true for columns, which can be seen by simply taking the transpose of the matrix. Before we can establish what happens with the determinant if we apply a row replacement operation, let's prove one technical fact. If a square matrix has two identical rows or two identical columns, then its determinant is equal to 0. Suppose A is a square matrix of size n, and let's say row S and row T are equal to each other. Then we are going to construct a new matrix B by swapping these two rows. These rows are the same, therefore matrix B is the same as the matrix A. In particular, they have the same determinant. But on the other hand, we know that swapping two rows in the matrix changes the sign of the determinant. This means that the determinant of B on the one hand is equal to the determinant of A, on the other hand is equal to negative determinant of A. Of course, the only way for this to happen is for the determinant of A to be equal to 0. The same also holds for columns, and to see this, we just take the transpose of the matrix. Now, we are ready to prove that the row replacement operation does not change the determinant of the matrix. The same is also true for columns. Suppose A is a square matrix of size n, and we construct a matrix B by multiplying row S of A by scalar alpha and adding the result to row T of the matrix A. Let's also construct a third matrix C from the matrix A by replacing row T of the matrix A with row S of the matrix A. Notice that these three matrices A, B, and C differ only in row T. Therefore, if we delete row T from all these matrices, we get identical results. With this in mind, we are going to compute the determinant of the matrix B by using the cofactor expansion along row T. The row T of matrix B was obtained by scaling row S of the matrix A and adding the result to row T of the matrix A. Now we are going to redistribute the terms and split this sum into two separate summations. In the first sum, we will factor out the scalar alpha. Next, let's recall that all the A, B, and C submatrices, which are obtained by deleting row T and any column, are equal to each other. And let's also recall that row T of matrix C is the same as row S in matrix A. But now you should recognize that the first sum is the cofactor expansion for the determinant of C along row T, and the second sum is the cofactor expansion for the determinant of A along row T. But this is not quite what we wanted to prove. We wanted to show that determinant of B is equal to the determinant of A. However, the determinant of the matrix C is equal to 0. Do you see why? It's because this matrix has two identical rows. Row S and row T of matrix C are equal to each other. And in the previous theorem, we proved that any matrix with two identical rows has 0 determinant. Now, the same result also applies to columns by taking the transpose of the matrix. If you found this video useful, then please give it a like to help others discover this content and subscribe to this channel to see more of these videos. In the next video in this series, we will apply this method we just discovered today to compute the determinant of a 4x4 matrix in a quick and efficient manner. I will see you later.